There are monsters out there, lurking in the dark. For centuries astronomers scanned the heavens again and again, without ever spying them. But behind the familiar stars and nearby calm galaxies of our universe lay something far more vicious, far more terrible, far more powerful. Completely invisible to the human eye, you would never see them even on the darkest of nights. Indeed, at first they appeared as nothing but distant, dim pinpricks of strange radio emission. But those pinpricks revealed something no astronomer could have ever expected. Something so strange, so bizarre, that for years nobody even believed that they could exist, that there must have been some mistake in our observations. Thankfully none are nearby, for if they were any closer they would flood us, our galaxy, our solar system, our planet, with deadly radiation. A single one of these monsters can easily pump out over 10 to the power of 40 joules every second. For comparison, our Sun outputs about 10 to the power of 34 joules, 1,000,000 times less, every year. The brightest among them outshine stars, outshine galaxies, outshine 1,000 galaxies at once. Some extreme events, like the most powerful supernovae, can briefly become brighter than these beacons. But those events are temporary, ephemeral, flaring and dimming in a matter of weeks. When these monsters awaken, they stay powered for millions of years. In just a fraction of their lifetime, they can easily produce more energy than even the most intense cosmic explosions. And they are hungry. They feed on anything, and are capable of tearing apart entire stars in a single fit of rage, producing flashes of radiation and jets of charged particles that shoot out for millions of light years, piercing through galaxies and spreading their destruction throughout entire clusters. They are the quasars, the most powerful engines in the known universe. But what drives these engines? What powers these lighthouses in the deep? The answer will take us on a journey through some of the most extreme physics in the universe, and even provide us with a grim warning. For though our galaxy is quiet now, it will not stay that way forever. The most distant quasar from us is 13 billion light-years away. It would take nearly the entire history of the universe to travel to, and that is without the universe expanding at the same time. Space is big and getting bigger, and sometimes that can make us feel small. At first, astronomers had no idea what they were seeing. By the 1950s, science had grown used to the idea of galaxies outside of the Milky Way, but even in this expanded cosmological view, the belief was that our universe was relatively small, only a few billion light-years across at most. And that expanded cosmos seemed relatively simple, even boring. There were galaxies, there were clusters of galaxies, there were vast expanses of nothingness. For a time astronomers were able to convince themselves that they were finally starting to figure things out. But in the mid-20th century there was a technological revolution. Optical telescopes, capable of seeing objects in visible wavelengths of light, were becoming enormous. And our ability to use the rest of the electromagnetic spectrum, wavelengths of light outside the visible, grew along with that. And with those new observations came the realization that the universe was far weirder than we could have ever imagined. One of the first revolutions was in radio. In the 1930s the pioneering engineer Karl Jansky solved the problem of how to reduce noise in sensitive radio antennae and discovered the first radio signals coming from deep space. Among the many bright and obvious sources, like Jupiter, the Crab Nebula, and nearby galaxies, astronomers also discovered numerous small, faint, distant point-like radio objects. These strange objects appeared all over the sky, emitted radio waves at a broad range of wavelengths, and could not be seen with visible or infrared telescopes. The only clue they gave was their position. They appeared both within the band of the Milky Way and outside of it. Since our galaxy is a thin disk, this meant that the sources had to either be extremely close, like the visible stars of the night sky, or extremely far away, like the distant galaxies. But if they were close, we should have been able to also see them in optical wavelengths. And if they were extremely far away, their intensity in radio wavelengths implied they were the brightest objects in the entire universe. Understandably, many astronomers pushed back against this interpretation, not only arguing about their distance, but also openly questioning what could possibly power something that bright. The disk itself glows, primarily at ultraviolet wavelength, but across a broad range of the electromagnetic spectrum. In addition, the disk constantly streams out showers of high-energy particles known as cosmic rays, electrons and protons accelerated to nearly the speed of light. Those microscopic bullets can occasionally strike a wandering low-energy photon at infrared or visible wavelengths, and when that happens, the particles transfer their energy to the photons, turning them into high-energy X-rays. The intense heat causes the cold atoms and molecules to unbind themselves, forming an electrically charged plasma, the same state of matter as lightning. Those rapidly moving electric charges around the black hole create a magnetic field, and very quickly it generates the conditions needed to power a dynamo, a seemingly infinite supply of energy that can turn a small magnetic field into something devastating. Initially within the disk, the magnetic field lines follow the motion of the gas, swirling in rapid circles around the black hole. But the innermost regions of the disk rotate far faster than the outer regions, forcing the magnetic field lines to coil up on themselves, storing up a tremendous amount of energy. The motion of the gas within the disk isn't smooth and steady. Instead, it's chaotic and turbulent, like a running river, with portions of gas clumping and colliding, waving back and forth as they swirl in the firestorm. When a clump of gas drifts away from the disk, it pulls on the magnetic field like a bit of string. But the difference in rotation from one section of the disk to another twists that loop of magnetic field around itself. The action of rotation eventually stretches that magnetic field line back down into the disk. This is a dynamo at work, which turns chaotic, turbulent motions in the disk into an increasingly strong magnetic field surrounding the black hole. Normally, magnetic fields don't affect the motions of matter, except in very small ways. But as the magnetic forces ratchet up within the accretion disk surrounding the giant black hole, they begin to dominate the motions of material. The closer the gas gets to the black hole, the more unstable the orbits become, and there is a certain special distance, known as the innermost stable circular orbit. Any gas that falls below that orbit is doomed. Most of the gas falling towards the black hole ends its life at the event horizon, never to be seen again. But some get caught in the twisting and winding paths of the magnetic field lines, their force is so strong that they channel and guide the gas as it falls. But how does this lead to the radar points we see in the distant sky? That is still a bit of a mystery. One hypothesis is called the Blandford-Znajec process, named after the two physicists who came up with the idea. The key to this idea is the fact that the black hole itself is rotating. When it does, it drags spacetime in the region around it, like moving a heavy coffee table twists the rug underneath it. This region, called the ergosphere, forces any object entering it to rotate along with the black hole. This includes magnetic fields. The strong magnetic fields within the disk punch in and out of the ergosphere, which forces them to twist up on themselves and punch above and below the spin axis of the black hole. The twisting fields create a tube of magnetic energy stretching above and below the black hole. While most of the charged particles following those magnetic field lines end up plunging below the event horizon, some just barely scratch the surface, accelerated by the extreme magnetic energies within the ergosphere. Following the lead of the field lines, the charged particles race away from the black hole in the form of long, thin jets of radiation, lighthouse beams racing out into the dark. As the particles travel along the length of the jet, they trace out circles around and around, a spiral pattern stretching for thousands of light-years. This radiation is primarily composed of radio waves, and it's here that we finally find the origins of the quasars. The loud radio sources observed by those early astronomers were powered by magnetized jets outflowing from supermassive black holes in the cores of galaxies, essentially acting like the universe's most powerful radio transmission towers. The particles in the jets are incredibly powerful, accelerating to nearly the speed of light. They race out of the galactic core and punch through the galaxy altogether, stretching for up to millions of light-years. Eventually, however, they lose steam, the particles interacting with the intergalactic medium that surrounds every galaxy. When they finally stop, they create a high-pressure zone of charged particles. These bubbles transfer heat all the way from the innermost regions surrounding the supermassive black holes into the volumes of entire clusters of galaxies, which can stretch for over 1 million light-years across. That is how powerful these systems are. Not only can they be seen from across the cosmos, but they can raise the average temperature of the entire galaxy clusters, the largest gravitationally bound objects in the universe. This picture, involving supermassive black holes, the ring of dust surrounding it, the ferocious accretion disk, and the magnetized outflows explain almost every observation of active galaxies. If we see the central core of a galaxy face on, we see the intense radiation from the accretion disk combined with the strong radio emission from the jet, and we recognize it as a quasar. If we happen to be looking directly down the barrel of the jet, then we get the most extreme emission, and we call it a blazar. It is like humanity first encountering cats in astronomical observations. Sometimes they see the whiskers, or a paw, or a swishing tail. Initially these seem like completely different objects, but over time we realize that they're really just different perspectives of the same kind of creature. But what of other active galaxies that aren't even loud in the radio spectrum? The solution here is that not every galactic core is active. To power a quasar, the black hole needs to feed. Without a supply of new material, the entire system shuts down. No gravitational collapse, no accretion disk, no twisting magnetic fields, no relativistic jets, no nothing. This picture also explains why we see no quasars in the nearby universe. Active galactic nuclei can last for incredibly long times. The longest-running quasars can run for over 1 million years. But they require constant streams of new material to feed their fires. The early universe was much smaller than it is today, with galaxies much closer together and undergoing frequent mergers. With every merger, new material finds its way to the center of the galaxy, setting off a feeding event, a new round of quasar activity. But today, with the universe much older and far larger, galaxy mergers do not happen often. With no new supplies of gas, we see no quasars in the local volume of the cosmos. Indeed, our own galactic core is quiet. Although Sagittarius A** hosts stars and gas and dust around it, it's a relatively empty region compared to the cores of the quasars. But this was not always the case. In 2010, astronomers using the Fermi Gamma Ray Space Telescope identified 2 gigantic regions stretching above and below the galactic plane, each one over 50,000 light-years across. The regions were filled with a thin plasma hot enough to emit gamma rays. Computer simulations revealed what caused them, a feeding event several million years ago. Whether a cluster of stars or a wandering clump of interstellar gas met its end in the hungry maw of Sagittarius A*, our black hole destroyed it quickly, shredding it into an accretion disk around the event horizon. And then the same physics went to work. The accretion disk energized a powerful magnetic field, which created jets and launched relativistic particles away from the galaxy, where they sit today. It seems that every galaxy has gone through at least one active phase, spending some of its life cycle as a quasar, with the central core of the galaxy, barely a few light-years across, outshining not just its own galaxies, but 1,000 galaxies combined. While the most powerful supernovae can outshine even quasars, it's only for a brief amount of time, a couple weeks at most. Quasars, on the other hand, can live for millions of years at a time. But despite our growing comprehension of the incredibly energetic forces powering these vast dynamos, the quasars we see are still too bright. The supermassive black holes that serve as their gravitational power source are also very, very big, too big. And they are not the only issues. Astronomers continue to discover quasars appearing in the earlier and earlier universe, too early. Quasars seem impossibly big and impossibly bright, existing impossibly early in the history of the cosmos. What does this mean? The quasar mystery. Everything about quasars is the very definition of extreme. The largest known supermassive black hole weighs over 66 billion solar masses. If you were to place that black hole in our own solar system, with its singularity at the center, by the time you reached the orbit of Pluto you would be less than 1% of the way to its event horizon. We currently know of around 1 million active quasars, and suspect that there are at least 10 million more in the observable universe yet to be seen, each one pumping out more energy than 1,000 galaxies combined, each one a fierce engine of plasma and radiation. And the quasars have been with the universe almost since its birth. The most distant known quasar, named J0313-1806, was firing when our universe was only 670 million years old, that's just 5% of its present age. But astrophysicists aren't quite sure how these black holes appeared so early, and got so big, in the relatively short age of the cosmos. There are hypotheses. One of the most widely accepted ideas is that they were created by the first generation of massive stars, when they exploded as supernovae and then collapsed under their own gravity.